Hi. My name is Joa. It's an unusual name. It's not Joachim, Johann, Joa, Joas. It's just Joa. And I did a lot of Flash development in the back in the days, but yeah, you know, Flash is dying and all that stuff. So I built a big online application, and we needed a way to convert it to the web. And that's why I started building a little project to compile Java bytecode to JavaScript. And first, let's have a look at the technology landscape. What I'm talking about today is mostly these question marks, because that's where all the magic happens. Everything outside is done by different tools. So we are actually here. Our tool is called defrag. And it takes Java bytecode. There are some other solutions as well. Wit, for instance, takes Java source code. There's Scala.js, which is tied to the Scala compiler. And there's JVM, which is the other project that's also using Java bytecode. And they all have different subtleties. And so most of those tools compile directly to JavaScript. Only Unity, for instance, who is compiling .NET bytecode, so to say, to asm.js. Yeah, asm.js, we don't do it because it's it would be fast, probably in Firefox, but in general, there's a big issue because there's no garbage collection, and you all know that Java is like JavaScript, a garbage collected language. And so we really bet on WebAssembly. I think this could be a huge opportunity, but whoever is sitting here and implementing it, please remember there's more than C and C++. I guess adding garbage collection to WebAssembly would also help Python, Ruby, and other implementations. Yeah, so we do everything ahead of time. So you could also choose to do this all just in time. The difference is that ahead of time means we take the Java bytecode and compile it to JavaScript source code instead of doing it at runtime, which means we could load the bytecode in the browser, and while the application is running, we could convert this to JavaScript code. So you could do it basically if you want to do it just in time. If you want to have executable code, so to say, you can simply create new functions from existing JavaScript source code. And you can apply a lot of different optimizations that we can't apply. You can make optimistic assumptions. You could say, OK, here is a class, and I know nobody extends this class, so I think it's final. You can invalidate those assumptions, which is called the deoptimization, which means you fall back to the slower version of your code. And you could also support class loaders, for instance. In Java, you could, at runtime, define a new class, load that bytecode, and do all that at runtime. Well, and in fact, it's feasible to do it right now because we have workers now. And the problem with the JIT compiling, especially in JavaScript, would be that you have all those optimizations, and executing them takes a lot of time. But you could do it in a worker, and if anybody's interested in doing that, I guess it would be a really interesting project. But we don't do it. We do it ahead of time because we want that the browser concentrates just on user's code. Because if you do it just in time, the browser would have to optimize your thing that converts to Java bytecode. Also, Java is statically typed, so we can apply a lot of optimizations already ahead of time. So that's a benefit for us. And we have a tracing compiler, which I'll explain in a second what that means. But basically, it means it goes through the call graph of your program, and it also knows that there, at this point, isn't a class extended by a different class. And in our case, because we don't just support JavaScript, but also other platforms, it's nicer because as long as the optimizations are done ahead of time, we don't have to write it in JavaScript and can apply to all different platforms. So how does the compiler look? What does it do? I hope you can see that. So I tried to simplify this as much as I could, but yeah, just a quick overview. Basically, the Java compiler creates a class file. Also, sorry that I'm talking so fast, but there is a lot of stuff we have to go through. So the class file actually is the first thing that happens is that it's read by our completer. In that case, what we call completing is reading basically the bytecode, which will give us a structure of the class, its fields and methods. And all those things can be read as well by a completer. And every time they are accessed, we resolve those symbols, which basically means the first method symbol we resolve is the main function. And from there on, everything else is getting resolved. So the function goes into a code parser, which basically creates a couple of graphs, and at the end exports a tree, which is kind of a legacy thing for us because we just went into a tree, and just the optimizer was going into a special kind of graph structure. But well, we want to get rid of this and do everything on this graph. But right now, we are in a tree form, go through some generic phases that modify this tree, and if the optimizer is enabled, well, we apply a lot of optimizations. If it isn't enabled, we apply most of those platform-specific phases that actually make the Java code run in the browser as JavaScript, which behaves like Java. OK. I want to give you maybe a little better example to understand how this looks. If you're a compiler writer, don't spoil the fun, because you will already know what happens. So that's like a simple method with a little loop. And it looks quite complex. So the first thing we do is we take the bytecode, split it into a graph so that we know what's going on, where's the stuff happening. And you can already see it goes from up here down into a loop and jumps back, and then comes the exit part that prints hello. And well, you know there are a lot of go-tos here and arbitrary jumps. So how do you represent those in JavaScript? Well, it kind of looks like this if you write C. So you can always do this stuff, and you can always do a goto in JavaScript as well. So labeled blocks considered evil. You can be the first to write that, and everybody will quote you afterwards. Anyways, from this graph structure, we also build a kind of a tree structure that gives us an information about how is the code actually structured, where is the loop, what are the blocks, how do they follow in a source code manner. And this is our first estimate of the JavaScript code. It looks horrible, especially if you look at the loop. You always generate a while true, which has a lot of break and continue statements. So fast forward like 20 phases, we can always apply a lot of simplifications and get rid of the break and continue statements and have a simple loop. And this is what we put into the optimizer. This is a simplified version of what it sees, which is again a graph. So we go graph to tree to graph, which is stupid, but another thing that we have to solve later. And the optimizer, well, does its stuff. It has a lot of knowledge about what's going on. And as you can see, it can get rid of a lot of stuff, especially in this example. And so when it gets out of the optimizer, we are left with this little piece, which basically says, well, the important part is here. It prints just 1. And the JavaScript code we then finally generate will look like this. And we also do some renaming, so it will probably, in the end, look like this, which is quite nice for such a big method. And well, the optimizer can prove a lot of stuff is unnecessary. And yeah, so that's what we want to achieve. So what's the big problem in all of this? Semantics. We have to implement all the JVM semantics in JavaScript. And there was a lot of stuff here. The lazy, OK, there's no timer. The lazy initialization. And yeah, I just quickly want to explain what all that stuff is. what we don't want to do is we don't want to add too much overhead, because that's what making the Java code, in fact, run slow inside of JavaScript. One thing is, for instance, the class initializer. The class initializer is always executed when a class is first being loaded in Java. So this is where all static variables are being initialized and all that kind of stuff. So when you write this kind of code in Java, what actually happens is that the base class of system, which is object, will get its initializer called, and then the system class will get its initializer called, but only if it hasn't been called before. So we kind of have to do the same when we compile this to JavaScript. And the most simple way to do it is, well, that you can add a property to your class, which simply does all this work. And we tried different aspects of what works best across browsers. This is the final solution. We also tried one where the method is redefining itself so that it just returns itself, but that didn't work out so great performance-wise. And in the end, this is the kind of JavaScript that we generate. So that's neat and tight. But there's still a problem, because if you run this stuff in a loop, well, now I would have 10 times, for instance, this call to the initializer. And the question is, can we prove that the loop is taken at least once? Because if we can prove this, which we can, of course, prove, is we can take the initializer out of the loop, for instance, and apply it just once before the loop. So if the loop runs 1,000 times, we don't have to execute the initializer 1,000 times. And this is very important stuff to do to make it fly, actually. And you can do even more. You can take the access of the system out variable out of the loop as well. And then you're pretty good, actually. You won't notice that this class initializer is actually running. There's another thing for instance initialization. When you have a class, all properties, like the X property, are initialized with a value. And we wanted to do it smart in the first, and we thought, OK, if you have more than 4 properties, I think, then we define a variable for this to minify the JavaScript that we output, right? And then we assign it to those things, because if you have like 50 variables or whatnot in a class, the code is smaller. But the problem is you learn that JavaScript VMs might guess the size of your object based on how often they see this.x equals y, not a local variable that is actually this equals something. So you're back to square one, because the JavaScript VMs, well, make a best guess. And that's like a counter example of what you can do. Numerics are a different thing. Long is quite boring. Well, in JavaScript, you have a long type that's well, already solved. You can basically put that in an object and say, I have the high part of the long and the low part, and I do all that stuff. And that's quite boring. But what's more interesting is the other simplifications you can do. For instance, if you have a method like give me the current time in milliseconds, and you cast that to an int, we implement current time milliseconds based on date now, which returns the double. So we cast that back to a long. So in fact, the method would look like this. You have date now, cast it to long, cast it to int. And you can already see where this is going, because it's probably unnecessary to create the long. So we have a method that converts the double to a long, and then we access the low bits of the long. But now we created an object that's totally useless. So what we want to do is we want to convert the double directly to an integer. And this is exactly what happens, and for instance, saves us the allocation of a long. So the main story is always simplify. Try to simplify it, make it as tight as possible, and get rid of everything that's not totally necessary. The integer, first we thought, yeah, we love integers, they're really cool. A plus B, it's simple, just add the OR operator, because the JavaScript integer is 32-bit, and you know you need the overflow when you do addition, multiplication, thanks to asm.js, well, we can now simply use integer multiplication. That's nice. And if you have a double, well, of course, just OR it. Well, or not, because, in fact, there's a subtle difference when you talk about doubles. And in JavaScript, for instance, if you have a double and apply the OR operator to the none value, you get 0, which is the same for Java. But if you have positive infinity or any value larger than the maximum integer, JavaScript, well, for positive infinity, JavaScript will give you 0 if you OR it. Whereas in Java, you will get the maximum integer. So all of a sudden, it's not that simple anymore to convert a double to an integer. So we had this little method written, convert a double to an integer, which did exactly that. And, well, we were quite, that was quite an interesting moment, because we had a benchmark, and we found an error in the benchmark because it didn't convert a double correct. So we implemented the method, and the benchmark was 10 frames per second, a little slower. And we thought, OK, well, this happened because we didn't convert a double correct. But you can already see that this method is a little bit stupid, because infinity is already greater than the maximum integer, and the negative infinity is already lower than the minimum integer. So we tried to change this method just a little bit, and all of a sudden, we get a 10 frames per second performance boost in V8. I don't know why this happens, but I guess somebody from the VR team could explain. And I guess it must have to do with the infinity values, that it treats it a little bit different, but you never know. So there's one last thing that we don't do, but that we will have to do eventually in the future, because the JVM allows you to, well, when you divide by 0, it throws an exception in, which is crazy, but it does it. And, well, in order to do that, you would have to have a method that checks if it is 0 or not and throw an exception otherwise, or you would have to well, prove that some value is never 0. Null pointer exception is also quite interesting, because I don't know anybody who's doing that at the moment. And basically, it means this. You have maybe a unit test where you do some stuff, and you say, OK, my tests only pass if a null pointer exception is raised. So how do you do this in JavaScript? The most obvious way would be to say, OK, I simply check if something is null, right? And then I raise an exception. But this is quite stupid if you have a lot of chain stuff. So you could also go and say, I create a method which does this null check for me. But that also doesn't scale very well. But the cool thing is, in JavaScript, well, you're basically free to do whatever you want to do. And, well, we can modify the prototype of type error to fit into our class system. And whenever we see a type error thrown by JavaScript, we already know that it's a null pointer exception, and it behaves just like the null pointer exception. So in our case, they are equivalent. And so the actual Java null pointer exception is, from the perspective of the application, always thrown just when the type error is thrown. Last little odd thing is undefined, because in Java you don't have undefined, but in JavaScript you have methods that return undefined. And this is also nothing new, but well, what does this print? It will be false, because undefined is not strictly equal to null, but it is non. So if I just have 2 of those, it would be true. And in fact, we always want to use strict equality, because that's more like what the Java operator would be. So when you do stuff like this, you would get a weird exception, because foo is not null, but it's undefined. If you use the strict operator. So you want to use the non-strict operator in those cases where a value can be null. Well, it's a little bit more complicated with strings and all that, because this would also cause now, when you compare a string and an object, to convert the object to a string, and we also don't want to have that. But in fact, when we implemented this, we got a 5 times improvement in a benchmark in Firefox. And the only reason that I could explain why this happens is because Well, if you do a strict equality check, if something is not null, it means that Firefox could think, well, you can still be undefined, so I don't know what to do. Whereas when you use the non-strict operator, it will definitely know that your object is, well, not null and not undefined. So maybe there is a hot path that can be triggered, and we were quite surprised that this actually happened, because I would have thought that the strict equality would be much simpler for a JavaScript engine. So what's the moral of the story? In the end, you want to write, well, when you generate JavaScript, you should mimic handwritten JavaScript so that to the browser, it should always look like a user has written the code, not like a machine somehow translated it. And you always have to clean up and simplify after you, because, well, otherwise all those semantics will slow your application down. How much time do I have left? Is there somebody who knows? Nobody knows. 10? Cool. And in the end, you should always also try to take shortcuts as much as possible, like with the type error. Abuse what's available, and, well, you have to test and measure your performance. And I can't stress this enough, because it applies also to everything that you do in normal JavaScript, which is you have to measure. So when you apply some optimizations manually, that's, well, if you don't measure what happens, it will be quite, yeah, well, surprising results can come out of this. So I just have 10 minutes, so I quickly skip over this. The optimizer, it does everything you would expect from an optimizer. There's some cool stuff. So when you write this in Java, well, usually we need for integer addition the OR operator, but in that case, we can already know that it will never overflow. So we don't need the operator, and we can simply use the increment. You could also prove it in this case, where you have the integer j that is growing with I. So you would also not need the operator, but when you look into the source of the JavaScript VMs, you will figure out that they also know this stuff, but they don't know it as good, which is probably because this happens just in time, and they can't spend as much time in all those analysis. So also, we don't do it for the browser, because the browser should think that it's still an integer. And this is also quite surprising, actually. When you write this in Java, Java will always create a new string builder for you and use the append function. So string concatenation here creates a string builder, and then append function, and then two strings, the string builder. So what we have to do for JavaScript, we have to find, there's a string builder and a lot of appends calls, so we can reconstruct the JavaScript string concatenation. And this one is one that's actually, it looks quite simple on the board, on the slides, but actually a lot of different optimizations have to play together. So this is the short iterator in Java. And the compiler and the bytecode will expand it to something like this, where you get the iterator from a list, and while it has the next element, you get the next element. And you write this kind of stuff a lot in Java code, so it would be nice to get rid of it. And actually we can, and we will generate this code based out of it. And what has to happen is the code has to be inlined. You have to prove that the iterator is not escaping the method. You have to know what values get into the iterator, what's taken out of it. And well, if you have all those 20 things ready, you're finally pleased with a result like this. And the cool thing is, if you do it in a generic way, it will apply to all of the code that you insert. And that's quite nice. So even if you write your own list, this would happen. But this is much, much easier when you actually have source code. Because in source code, you just see this special kind of loop, and you know, oh, OK, I don't, I generated different. So yeah, that's not so smart in bytecode. Last but not least, I think quite a cool optimization is tail recursive optimization, where you can prove that, well, if you like to write code in a functional style, you can actually let the compiler transform that back into a loop, because it can know that some stuff is in a tail position. So we can rewrite it into a loop, simplify the loop, and have a final result like this. So most browsers don't do this, but they do most of the normal optimizations that you would expect. So actually optimizing your JavaScript code by hand isn't something that you should necessarily do anymore these days. And last but not least, WebIDL. So we compile that to Java. This is what WebIDL looks. It's basically what all the browsers use to generate their C bindings. So there's some Java code that comes out of it. And the question is, which one do you use? Blink, Servo, Firefox, they all have their own WebIDL with very own extensions. If you do this stuff, and if you compile all the WebIDL and test it actually in the browser for once, in different browsers, you will run into an enormous amount of spec bugs and inconsistencies. And it's just annoying. And yeah, workers, also quite interesting, because the JavaScript we generate can be directly fed into a worker. And we learned that, well, most of the time you can simply say, instead of the window, just use the self variable. That makes a lot of sense. But also, we were quite surprised that we always have to check for types. So if you, for instance, have some code like this in a worker, in strict mode, you will immediately get an error like this. So for some reason, error event isn't defined in a worker. You have the XML HTTP request, but you don't have an error event. So for instance, when we have an instance of check, now we always have to generate some stuff like this so that it works immediately in a worker. And so that's it mostly for the compiler. I also wanted to talk a little bit about the framework we built around it. One is the display list. I think I said I did a lot of Flash work back in the days, and what was really cool about Flash is that you had a display list where you could simply arrange stuff and move it around. So we wanted to have that too. And basically, I think there are a lot of frameworks that do something similar, where you have a tree-like structure, and you can arrange all your objects. And again, you can apply like the same ideas that you use for optimizing code to something that happens at runtime. So we don't want to walk a tree all the time when we render some stuff to WebGL. So we want a flat representation. And we do that by basically concatenating all this stuff together in a kind of, well, specialized structure. But in that case, we also cache like all the information of the vertices, where they would go on WebGL, and this is quite a costly thing. So again, this is what an optimizer would do as well. It has to figure out, okay, does it make sense to apply an optimization at the time, or does it not make sense? So we have this mode where we render simply in a bulk mode, and we just put all that stuff to the graphics cards. Oh, just 2 minutes. And or just go and yeah, cache all the vertex information and the culling information so that you get really fast results. Okay, we rushed through the slides. So I wanted to show you some demos. This is for the display list. I hope it works. So in that case, you could see that just one object is moving, so the display list would switch to this caching state, and when everything moves, it goes into a bulk rendering state. So this is nice for applications as well as games, right? So you can you get best of both worlds. And this was the double thing, where it went 10 FPS slower because well, it used this infinity thing. So instead of those 50 frames, we were at like 40 frames. And because I'm out of time, I just want to show you this real quick, because we did a lot of the WebIDL stuff, converted it to Java, and then those guys from which I was working on earlier converted this big Flash application audio tool to Java, and then we compiled the Java code to JavaScript, and I hope I've got some internet, but I don't. Well, that's too bad. No internet. Okay, maybe it loads in the end. So, because what I wanted to show you is that, well, this is just a smaller version of the whole thing, and speed-wise, we have enough speed now to generate real-time audio in JavaScript and render all that stuff on a graphics card. So I can do all this, well, tweak a lot of stuff, and it does this all in real time. And so this is like one of the cool things now, that we have the ability to take the existing stuff and compile it to JavaScript. There's also another one. So we also had that in Flash. Actually, that's now all running, so that's just pure JavaScript. And it's also at runtime parsing old Amiga mod files and generating the audio. So basically, there's a lot of computations, and you can play your old favorite music. Okay. So let me see if this last. Nope. Okay. No. So the cool thing here is, come on. So this is actually has built-in WebRTC and live collaboration. Okay. So I talked about the guys from Audio Tool. They are now all here. You can say hello. Okay, hello. They don't see you, but and so this whole application is now running in a browser, and via WebRTC they can actually move everything around, do some stuff. So I don't have to do anything right now, and they can make some music. You have to be quick because I'm already out of time. So if you know the Flash application, this was actually quite a big thing, because so here we have WebGL that's running very smooth and very nice. And I can turn all the knobs, do all this routing. And for me, the cool thing is to see now that we basically have this running in the browser without Flash. And it was like a big struggle to get us running in Flash. So we implemented our own garbage collection because the Flash player was so well, bad. And a lot of things to get this working. Okay. So I'm now actually not doing anything, because they can all do it in the live collaboration, and which is done via WebRTC. And you can even hook your MIDI stuff to it. And I think it's quite great, because it really shows that the browser is now capable of, well, of supporting like even applications that are very demanding when it comes to resources. And it absolutely proves that you can do whatever you want now in a browser. It even feels like a real application. We have this timeline here, and which you can. I have to exit this mode. Okay, so this was something that we never did in Flash, because you can simply undock the timeline. So when you have a second monitor, you can now split that application, you can close it, and it flips just right back. And this is, well, actually simply amazing. Okay. Yeah, thank you. Okay. Yeah. So I guess I'm done. Yeah. Thanks. Thanks for listening. And well, if you have any questions, feel free to come by. Thank you.
Big thank you.